All right, welcome back, everyone. Today we're digging into a topic that's absolutely fascinating, and honestly, kind of a giant puzzle. We talk all the time about how crazy capable large language models, or LLMs, are getting, but there's this massive, underlying question that engineers and researchers wrestle with every single day. How do we systematically test and evaluate these models? I mean, when an AI generates an essay, or writes a complex block of code, or answers a tricky query, who or what actually decides if that output is any good? Well, today, we are unpacking a high-fidelity analytical pipeline designed to do exactly that.
Which brings us straight to the big dilemma. How do we actually grade an AI? Here's the reality. As LLMs evolve at literal lightning speed, relying on human grading is just simply too slow. It's incredibly expensive and frankly impossible to scale. Think about it. If a model generates 10,000 responses in an hour, humans can't possibly sit there and read every single one to figure out its quality. So this creates a fascinating challenge. We know we need automated systems to grade AI, but how do we build an automated grader that actually understands nuance the way a human would?
So, let's look at our roadmap for this explainer. We're going to start with the AI grading dilemma, break down the pipeline architecture, compare rule-based versus model-based grading, uncover some systemic biases, and wrap up with the future of AI evaluation. Let's get right into it.
Starting off with Section 1, the AI grading dilemma.
The developers behind this pipeline really set out to investigate 4 core pillars. First up is human alignment. Basically, if an automated metric gives an AI an A+, would a human actually agree with that? We absolutely need these metrics to correlate with human ground truth. Second is evaluation efficiency. There is a massive trade-off between how fast you can score an output and how qualitatively accurate that score actually is. Third, and this is super interesting, is systemic bias probing. We're looking for unfair grading advantages where the system might just be getting tricked. And fourth is failure mode analysis. We need to find those weird edge cases where automated metrics totally fall apart, like confusing basic semantic correctness with syntactic similarity.
Moving right along to Section 2, Pipeline Architecture Explained.
Let's step into the technical arena and see how this thing actually builds out. The workflow here operates in 3 distinct steps. Step 1, data. The pipeline ingests the first 100 instructions from the Alpaca Eval dataset, ensuring we've got high-quality, diverse prompts to test with. Step 2, generation. The pipeline uses the Hugging Face API to have a model called Zephyr 7B Beta generate responses to those 100 prompts. Then we hit Step 3, scoring. Everything flows into an analytical engine, specifically a Jupyter notebook called evaluationanalysis.ipynb, which crunches the data, runs the evaluations, and calculates the final granular statistics. It's a clean, linear, and highly effective structure.
Now, a quick but crucial detail. This entire setup is built in a fully containerized environment using Docker Compose. What that means is zero dependency conflicts. You literally just run docker compose up build, and the system pulls in Python, JupyterLab, transformers, and scikit-learn exactly as intended. This means anyone, anywhere, can reliably reproduce these exact tests without running into nightmare software clashes. And as you probably know, perfect reproducibility is the absolute gold standard in AI research.
All right, Section 3, and this is kind of the main event, rule-based versus model-based.
Imagine a head-to-head matchup between 2 totally different grading styles. On one side, you've got rule-based metrics. Think of this like a really rigid Scantron test. It uses exact word matches and n-gram overlaps. So if the AI doesn't use the specific words we expected, it fails. It's incredibly fast, super low latency, but painfully literal and completely lacks nuance. On the flip side, we have model-based metrics. This is way more like a teacher grading an essay. It actually uses another LLM to read the response for qualitative accuracy and actual comprehension. It's quite a bit slower to run, sure, but it catches the underlying semantic meaning, not just surface-level words.
So, this table captures the crucial breakdown of these categories. For rule-based, it's using Rouge and Blue to calculate precision and recall purely on exact n-gram overlaps. Stepping up in complexity, we have an embedding-based metric called BERT score. This uses a model called Robert to Large to match contextual embeddings, meaning it's looking at high-dimensional semantic similarity. And finally, the pure model-based approach, LLM as a judge. Here, the pipeline uses zero-shot prompting, asking the Zephyr 7B beta model itself to read the output and give it a qualitative score. It's literally an AI grading an AI.
Which brings us to Section 4, uncovering systemic bias.
Now this is where things get super interesting. When machines grade machines, we start seeing some really weird quirks, like verbosity bias. The pipeline actively quantifies this.
Verbosity bias is a systemic flaw where an LLM acting as a judge will unfairly favor a longer, wordier response, even if the actual content is pretty mediocre. It's basically the AI equivalent of a student padding a 5-page essay with pure fluff just to hit a word count, and the AI teacher handing out an A just because it looks heavy. We absolutely have to identify and adjust for this if we want reliable, automated scoring.
On top of that, the pipeline generates a failure analysis report to spot those edge cases where these metrics drastically diverge from one another. Just imagine an AI gives a perfectly correct answer, but uses synonyms instead of the exact terminology expected. The rigid key of a rule-based metric like BLUE is going to look at the syntactic similarity, see different words, and immediately fail the AI. But the brain of a model-based judge will look at the semantic correctness, realize the meaning is completely identical, and pass it. Understanding these discrepancies is critical to knowing which grading tool you can actually trust.
And that brings us to our final section, Section 5, the future of AI evaluation.
By running all of these, the rule-based, embedding-based, and model-based algorithms, and comparing their summary metrics and bias stats against a simulated ground truth dataset, researchers are essentially mapping out the frontier of reliable evaluation. The ultimate goal here is pure human alignment. We want to find, or build, an automated metric that perfectly mimics human intuition and qualitative judgment, but operates at the lightning speed of a machine.
I want to leave you with this thought to ponder. As AI models write more of our code, draft more of our emails, and frankly, synthesize more of our world's information, who or what should be trusted to grade their work? We certainly can't do it all ourselves anymore, but as this pipeline shows us, the automated systems we build to do the grading have their own inherent biases and blind spots. Understanding this underlying architecture is the absolute first step in ensuring the AI tools we rely on every single day are actually as smart as we think they are. Thanks so much for joining me on this explainer, and keep questioning the algorithms.